So let's continue from the last lecture where I left off by highlighting or some questions that we need to resolve about ideals before we can start doing arithmetic in terms of ideals completely instead of doing it in terms for numbers. So in order to do arithmetic over ideals, we have to define arithmetic over ideals. So let's just do that first. So as usual, we start with a ring, a commutative ring, and let's collect all the ideals of this ring in the set R sub I. So now we are treating each ideal as an element, and now we would like to do arithmetic exactly as we do our ring. So what are we again have to go through the properties of the ring and see if those properties hold here. It must be a commutative group under addition. That's the first thing we need to ensure. So the first step is to define addition of ideals. So let's say we have two ideals in Ri. And the definition is as you would expect in the most natural way, that the addition of the two ideals is simply addition of elements of ideal. I1 plus I2 contains all the elements of the form A1 plus A2, where A1 is in I1 and A2 is in I2. Now the result must be an ideal of the ring. That is very important. So the question is this set an ideal of the ring? Think about it. Answer is straightforward. It is indeed an ideal of the ring. Why? For ideal property, we have to satisfy two conditions. That if you have two elements from I1 plus I2, their sum must also be in the same ideal. So if A1 plus A2 plus A1 prime plus A2 prime, these individually are elements of this ideal, then their sum is, I can write as A1 plus A1 prime plus A2 plus A2 prime. A1 plus A1 prime is in I1, A2 plus A2 prime is in I2, and so their sum is in I1 plus I2. The second property is that you multiply any element B from the ring to an element A1 plus A2 of this set, the result must be in I1 plus I2. And this also is seen very easily. B times A1 plus A2 by distributivity property of multiplication is BA1 plus BA2. Now since A1 is in I1, BA1 is also in I1. Similarly, BA2 is in I2, I1, I2 being ideals. So this is in I1 plus I2. So we have defined addition of ideals very simply. So this shows the closure property. For not only defines the addition, it also shows the closure property of addition. Now we have to verify other properties. Commutativity is straightforward. It's just because the ring addition itself is commutative, so I1 plus I2 is same as I2 plus I1. Then identity, what is the identity here? That's important. What is the identity? So identity must be an ideal, the additive identity, the 0. So what should that ideal be? Ideal of 0. What is ideal of 0? Yes. What does it contain? Singleton set, just a 0. Absolutely. And so I plus 0, this is the ideal of 0. This is the notation I defined earlier, right? This is I, because you are just adding 0 to every element of I, which is I. That's done. So identity is defined, and now how about the additive inverse? Inverse of? I is inverse of itself. Yes. Why?
I1 plus I2 contains I1.
I1 plus I2 contains I1. Because 0 belongs to any ideal. Is that correct?
But then if inverse, if we hope to find an inverse.
Oh, there is a problem with inverse. 0 does not belong. 0 does belong to every ideal. You see, 0 times an element is 0, and that must belong to the ideal. Similarly, your minus A must also belong to the ideal, because you multiply with minus 1 every element, that should belong to the ideal. So if A belongs to ideal, minus A also belongs to the ideal. So then is I in inverse? That is I plus I 0? It's not. I plus I is not 0. It will contain 0, but it's not 0. Correct? So we have a problem. We have a problem in that this is not really a group under addition. It has closure, it has commutativity, associativity also pretty much follows. It has an identity, but it doesn't have an inverse. So that is something we lose already. Fortunately, it is not a big loss. Because you see, why are we interested in these looking at the ideals? To get the unique factorization. So the situation here in terms for ideals is same as the situation of positive integers. Set of positive integers, or non-negative integers I should say, they also don't have inverse. But the factorization, prime factorization, does hold over the set of positive non-negative integers. Isn't it? So we don't really need the additive inverse for the carrying out the prime factorization kind of operation. So we don't worry about it. We have the requisite properties that we need. Fine? So that is what the addition works as. Now multiplication of ideals. How about that? How do we define multiplication of ideals? If you try to define it, let's say I1 times I2 is in the exactly the same way A1, A2, where A1 is in I1 and A2 is in I2. And let's ask the question, is this an ideal? I1 is closed under multiplication, so this is contained in I1, surely. It is also contained in the I2. That's very correct. So this is contained in I1 intersection I2. That's a good observation. But is it an ideal?
From I1, the minimum element which represents the ideal I1, into the minimum element which represents the ideal I2. The ideal of that multiplication of that.
If there is a minimum element representing the ideal. But we have seen last time that is not true for all ideals. Yes, exactly. That's the problem. And you multiply any element of the ring to this, you stay within this. That is not a problem. But if you add two elements of this, A1, A2 plus A1 prime, A2 prime, it's not clear if it is an I1 in this set. So this definition doesn't quite work. So how do we define the product of two ideals? Suppose I define it this way. This is cheating actually. This is forcing the product to be an ideal. Just by saying, I would like in I1 times I2, this ideal, to contain all products A1 of the form A1, A2. But that set may not be an ideal. So let's pick up the smallest ideal that contains this set and define that to be I1 dot I2. Okay. Question is this definition sensible? Is there really a smallest ideal? Or are there multiple ideals containing this set which are not really comparable to each other? Fortunately, we have a lemma which says that if I1 and I2 are in Ri, then their intersection is also an ideal. Why? Again, proof is pretty simple. If two elements are in the intersection, I1 intersect I2, their sum is also in the intersection. Because these two elements are in I1 as well as in I2, so their sums would be in I1 as well as in I2. Similarly, take an element of the ring, any element of the ring B, and multiply it with an element of I1 intersection I2. Since it is in I1, so the product will be in I1. Since it is in I2, the product will be in I2. So therefore, it is in both I1 and I2. So proof is immediate. And this lemma ensures that there is indeed a smallest ideal that contains the set. Because if there are more than one ideals containing this set, their intersection will also contain this set. And that is also an ideal, which is a smaller ideal than these two individually. So you can keep taking intersections, essentially take all ideals that contain this set, take their intersection. That's an ideal, and that's the smallest ideal containing. There is another very nice characterization of this ideal, I1 dot I2. It is the elements of the following form, which are finite sums of products of elements of I1, I2. And now you can directly verify that it is an ideal. Take two elements of this form, add them, that will also be an element of this form. Multiply any arbitrary element of the ring to an element of this form, that will be an element of this form. Okay, so it certainly is an ideal. It certainly contains this set, and it is the smallest set containing this, because if this is contained in any ideal, all finite sums of elements of this form must also be contained in that ideal, because that ideal must be closed under addition. So certainly this is also contained in that ideal. So this proof is also immediate. Okay, so that's multiplication of ideals. That's a good question. Not always. This is always contained in I1 intersection I2. Why? Because this is contained in I1 intersection I2. I1 intersection I2 is an ideal, and this is the smallest ideal containing I1 containing this set. Therefore, this ideal is contained in I1 intersection I2. But it may be equal to I1 intersection I2, it may not be equal to. So we have now the definition of multiplication of ideals. Now again we need to verify the properties of multiplication and see for multiplication what is the closure is already defined, commutativity is clear, associativity is clear. How about the identity? What is the identity here? The whole ring. The whole ring is, yes, actually I1 multiplied with 1 is I. This ideal is equal to the whole ring. Whenever 1 is an ideal, then that ideal equals the whole ring, because then you multiply every element of the ring, you get those elements. So this is the unit of multiplication. And for multiplication, we anyway don't need an inverse, so we are quite fine with that. The final property is a distributivity of multiplication over addition. Right? So we have to see that I1 times I2 plus I3, what is this? Does this property hold?
So I1 dot I2 plus I3 are finite sums of that.
Yes, so let's just write down what is the general element of this. General element of this would be A1 or sigma, yes, J, A1J times A2j plus A3j. Correct? This is just multiply out and you get sigma or j A1j times A2j plus A1j A3j. This is an element of I1, I2. This is an element of I1, I3. So whatever, all the elements of this are contained in this. How about the other way around? Same way. So let's take a general element here. Let's use a different color pen. This is sigma over j A1j A2j plus sigma over I A1I A2I. Oh, sorry, A3I. Can I write it in this form? No? Cannot write? Why not?
One element is common. It's not necessary
That element is common here and here. But there is a simple trick to get around this. Just write this. Okay, just write this as plus 0. 0 plus. See, this is, and then combine these two sums. This is an element of I2 plus I3. This is also an element of I2 plus I3. And then you're multiplying elements of I1 and then summing up. There is a finite sum. It's just a very trivial way of ensuring that this is equality. Fine. So that establishes this distributivity property, and that's very crucial, because when you factoring out that there is something that you need this property to hold. Good. So we have now established arithmetic over ideals. Okay. And since we have established arithmetic over ideals, we can talk about, given an ideal, writing it as a product of other ideals. Now in order to complete the picture, we also would need to define the notion of prime ideals. That's what we would want, that prime ideals should be ones which cannot be factored into smaller ideals. So what should that definition be? Make a guess.
I equal to I1, I2, and either I1 is multiplicative identity or I2 is
Yeah, whenever.
So then either I1 or I2 is ideal of 1.
Either I1 or I2. Okay, that's a good guess. That does make sense. It mimics the property of prime numbers. There is another way of defining prime ideals, which is I is a prime ideal if any ideal, every ideal, for every ideal J which contains I, either J is equal to I or J equals the whole ring. This is somewhat not so intuitive definition of a prime ideal. What is the relationship, if any, between these two? Can you think about it?
When we say I equal to I1 plus I2, then I1 and I2 are supersets of I. And then
I1 and I2 are, no, wait a minute.
I mean I1 and I2 are supersets of
I1 times I2.
and then we are kind of saying that if I is equal to jk, then j equal to I or j equal to r.
If I is equal to jk, then
J equal to I or j equal to r
yes,
is the second definition.
yes.
First definition was
I will give this as a small exercise for you to work on. So in the next class we will come back to this, because I want you to think a bit about these types of reasonings and see what you come up with.
I1 and I2 contains, from the previous definition, I1 and I2 is a subset of I1. Is a subset of I.
I1, I2 is both subset of I as well, I1 as well as I2.
I2.
Yes.
So we can say that it's either subset of I or subset of, they are subsets of I and subset of R.
Work it out. Think about it at leisure. We are meeting tomorrow again, so we'll continue with this tomorrow morning. Okay. So we have in either case, we have defined the notion of prime ideals. And now we pose that same question in terms of ideals. What does the question translate to with respect to the factoring or expressing an element of the ring in terms of as a unique product of prime elements? That we cannot do. That's why we move to the ideals. So an element of the ring in terms of ideal corresponds to, and that I should define actually. I have been holding on to that definition for a while. So I want to give a name to this special kind of ideals which are generated by a single element of a ring. So these are called principal ideals. Okay. And now the question of uniquely factoring an element of the ring in terms of prime elements translates to uniquely factoring a principal ideal which corresponds to the element as a product of prime ideals. Okay. And that, as I've been saying, can be shown that for certain kind of rings which are called Dedekind domains, every ideal, not only a principal ideal, every ideal can be uniquely expressed as a product of prime ideals. That's a theorem I will not prove, so just stated it, I'll write it down also, but let's more interestingly look at an example. The one we got stuck with, and that's where the whole discussion started from. The ring z square root of minus 5. In this ring, we had 2 times 3 equals 1 plus square root of minus 5 times 1 minus square root of minus 5, right? And 2, 3, 1 plus minus square root of minus 5 all are irreducible. We have seen this. I think I have not given a proof that these are irreducible elements, but I did ask you to work this out. And using the notion of norms, you can very easily show that all of these elements are irreducible. Okay? So, these are irreducible elements. So, there is a unique factorization property breaks down in this ring. And now let's look at the corresponding ideals and see what we can say. So, first, let's look at the ideal of 2. Ask the question, is this a prime ideal? Answer is no. The principal ideal 2 factors as the ideal 2 1 plus square root of minus 5 times this ideal itself. So, it's a square of an ideal. Let's see this. What are the elements of this product ideal? All finite additions of products of this kind. What is the general element of this ideal? 2 alpha plus 1 plus square root of minus 5 times beta. You multiply this with another element from this. That's the same ideal here. So, let's say 2 gamma plus 1 plus square root of minus 5 times delta. What is this equal to? Is this. Just multiplying out everything. You see this. Now notice that every term here is an even multiple. That is, I can write this as 2 times 2 alpha gamma minus 2 beta delta plus alpha delta plus beta gamma plus beta delta 1 plus square root of minus 5. Now, inside the square brackets, we have an element of the ring. Not the ring, but it is actually an element of this ideal. Correct? This part is even. So, that's a 2 times something, and this is just a multiple of 1 plus square root of minus 5. So, this is an element of this ideal. It's actually, it doesn't have to be, it's enough that it's an element of the ring, because then if there is a multiplier 2 outside, which puts it inside this ideal. Correct? Now, any finite sums of this form will also be even multiples, and therefore that will also be an element of the ideal, principal ideal generated by 2. Okay? So, this shows that all elements of this product ideal are contained in this ideal. How about the converse? That's converse is trivial. Why? Any element? No, so for the converse I had to show that every even number, that's this principal ideal, is contained in this ideal. In particular, let's try to show that 2 is contained in this ideal. If I show that 2 is contained in this ideal, then I'm done. So why is 2 contained in this ideal? Take beta, gamma, delta to be 0. Then this is 0.
Can't show that 2 is contained in this. If we will take, already we have 2 is common, so we require that 2 gamma, alpha gamma minus 2 beta should be equal to 1.
That should be equal to 1.
And if we will take 2 common, then what the sum, that should be equal to 1. No, that should be equal to 1 by 2.
That's right.
That's
Not possible. Yeah, actually that's true. So my claim is wrong, that means. Unless I have missed out something. Let's see in these calculations. What it shows is that 4, the principal ideal of 4 is contained in this. But is contained in this, but that's not equal to this anyway. So what's going wrong here? So let's stop here, and I'll leave this also as a bit of an exercise for you, and tomorrow when we meet, we'll fix this, and we'll also discuss those 2 alternative definitions of prime ideal.